Hi everybody. In this video we're going to look at a group as order p squared. And so far we don't know anything about groups of order p squared other than that they have order, well, p squared. We're going to assume that there's some element in G called x that has order p, and then some other element in the group, call it G, which is not a power of x. So x generates p different elements. G is not one of them. And we're going to assume that this G commutes with every element in the group generated by x. So that means that if I have some x to the I times G, it's the same thing as if I write it in the other order. I have some G times x to the I. Okay, now what we want to prove is that G, well, we already know it commutes with every power of x, but we actually want it to commute with every element in the group. So the way we can proceed here is by recalling that if you look at the centralizer of this element little g, that is all the elements in G that commute with little g, so all the z in G such that gz equals zg, that this is a subgroup of G. Once you know it's a subgroup, then Lagrange's theorem applies. And we know that the order of the centralizer has to divide the order of G, which is equal to p squared. So that immediately tells you that the size of the centralizer is 1p, or p squared, the only divisors of p squared. Okay, but we can rule some things out pretty quickly. For instance, we know that it's not 1. Why is it not 1? Well, we know that this little g commutes with every element in the group generated by x, which contains p different elements, because x had order p. So the centralizer has more than one element, since G commutes with at least p elements. With at least p elements. Namely, the elements in the group generated by x. Okay, so it can't be 1, so it's either p or p squared. Well, p sounds pretty good because, hey, we already know G commutes with the p elements in the group generated by x. But G was assumed to not be one of those p elements. And G certainly commutes with itself, right? How's that for a deep insight? Which means that G is also an element in its centralizer, but it's not one of the p elements that we already know, which tells you that the size of the centralizer is at least p plus 1. There's at least p plus 1 elements because I have all the powers of x and I have G. But it can't be p plus 1. In fact, now we know it can't be p, so there's only one thing left. It's got to be p squared. So that tells you that the centralizer of G has order p squared, but that's the order of the group. So that tells you that the centralizer of little g is equal to G. But that means every element of G commutes with little g, which is what we wanted to show. Now, a little footnote to this video. This is actually going to be very useful when we prove that every group of order p squared is abelian. And I'll outline how that works here. So we're going to prove later on that if G is any group, we call them p groups, whose order is a power of a prime. So if G is a p group, i.e., well, we'll take this just as our definition for finite groups, that the order of G is some power of a prime p, then the size of the center is not 1. Okay, there's at least one non-identity element that commutes with everything. Okay, so in the special case where the order of the group is p squared, then we know that the size of the center, well, originally just by Lagrange's theorem, it's 1p or p squared, but it's not going to be 1. So it's either p or p squared. If it's p squared, that means that the center of the group is the entire group, and G is abelian. So if the center of the group has p squared elements, then the center of the group equals G, which implies G is abelian. Okay, so what if it's this other case? What if the center of the group has p elements? Well, then there's some element in the group which is not in the center. So there exists some G in G such that G is not in the center of G. But what's the centralizer? Well, this is exactly the situation as above. The centralizer of this little g, we know that it at least is as big as p, since everything in the center of G commutes with little g. But of course, again, little g commutes with itself, so this is at least p plus 1. By Lagrange's theorem, it must be actually all of p squared. All right, so the size of the centralizer must be p squared, which means that the centralizer of little g is equal to g, but that means that g commutes with every element. Well, that means g is in the center. A contradiction. So this tells us the only case we actually have is when the center has size p squared, i.e. the group equals its center or the group is abelian. So all groups of order p squared are abelian. That's not too shabby.